What if everything you think you know about time is wrong? What if the past, present, and future are not separate, but happening all at once? Einstein changed the way we see reality, but modern physics goes even further into black holes, quantum chaos, and even possible multiverses. Stay with me, because by the end of this video, your understanding of reality may never be the same again. Since the earliest days of human thinking, people have tried to understand two mysterious things: time and space. These are not objects you can touch, yet everything that exists depends on them. At the simplest level, time is the way we measure change. When something moves, grows, ages, or decays, we say time has passed. Early humans did not have clocks, so they relied on natural signs such as the rising and setting of the sun, the phases of the moon, and the changing seasons. For them, time was not a straight line moving forward, but something that repeated in cycles like day and night or summer and winter. Space, on the other hand, is the place where everything exists. It is the distance between objects and the container of the universe itself. Ancient people understood space through what they could see, such as the sky above them, the land around them, and the stars, which they believed were fixed in position. To them, space seemed unchanging, like a stage on which all events take place. As human thinking developed, philosophers began to explore these ideas more deeply. Greek thinkers like Aristotle believed that time is closely connected to motion and that without change, time would not exist at all. He also viewed space as a fixed and stable background where everything happens. Plato, another important philosopher, thought of time as something linked to the heavens and even connected it to a higher, more perfect reality. In other parts of the world, such as ancient India and within Islamic scholarship, scholars developed their own ideas. They often saw time as something vast, possibly infinite, and sometimes cyclical. Space was understood as part of a larger cosmic system that followed certain rules. Islamic scholars, such as al-Biruni and Ibn Sina, studied motion, the nature of existence, and how time is related to events. They suggested that time is not just a simple flow, but something deeply connected to the existence of things themselves. As these ideas continued to develop, a major question began to take shape. Is time something that truly exists on its own, or is it just a way for humans to understand change? Along with this came another question about space. Is it simply empty, or does it have its own kind of reality? These questions were not easy to answer and remained open for many centuries. Even without modern science, early thinkers were building the foundation for future discoveries by asking fundamental questions about reality, the universe, and our place within it. Over time, this curiosity led to a shift from philosophical thinking to scientific investigation. During the scientific revolution, thinkers began using mathematics and experiments to study time and space in a more precise way, marking the beginning of a new and transformative chapter in human understanding. The understanding of time and space took a major turn during the scientific revolution in the 17th century, especially with the work of Sir Isaac Newton. Before Newton, ideas about time and space were mostly philosophical, but he introduced a mathematical and scientific way to describe them. Newton proposed that time and space are absolute, meaning they exist independently of everything else. According to him, time flows at a constant rate everywhere in the universe, unaffected by anything that happens. Whether a person is moving or standing still, whether they are on Earth or in space, time passes in exactly the same way. In the same way, Newton believed that space is fixed and unchanging, like a giant stage where all physical events take place. Objects move within this space, but space itself does not change or react to them. Newton's ideas were powerful because they allowed scientists to predict motion with great accuracy. Using his laws of motion and gravity, he explained how planets move around the sun, how objects fall to the ground, and how forces affect motion. In this system, time acts like a universal clock, ticking the same for everyone, and space provides a stable framework in which everything exists. This view made the universe seem like a well-organized machine, where everything follows clear and predictable rules. For many years, This model worked extremely well and became the foundation of classical physics. However, not everyone fully agreed with Newton's view. Another philosopher and mathematician, Gottfried Wilhelm Leibniz, argued that time and space are not independent things, but instead depend on the relationships between objects. According to Leibniz, time is simply the order in which events occur, and space is the arrangement of objects relative to each other. In this view, if there were no objects or events, then time and space would not exist at all. This created an important debate between two different ways of thinking. One where time and space are real and independent, and another where they're only meaningful because of the things within them. Despite this debate, Newton's ideas remained dominant for more than 2 centuries because they matched observations and experiments very well. Engineers, astronomers, and scientists used his laws to build machines, calculate planetary motion, and understand the physical world. The concept of absolute time and space became deeply accepted, shaping how people thought about the universe. It gave a sense of certainty and order, making it seem as if the universe operates like a perfectly designed system with fixed rules. That never changed. Yet, as science advanced and measurements became more precise, small problems began to appear. Certain experiments and observations could not be fully explained by Newton's framework. These issues were not obvious at first, but they slowly raised doubts about whether time and space were truly as simple and absolute as Newton had described. This set the stage for one of the greatest revolutions in science, where the very nature of time and space would be challenged and redefined in a way that no one had imagined before. The early 20th century brought a dramatic shift in how scientists understood time and space, mainly through the work of Albert Einstein. He challenged the long-held belief that time and space are absolute and unchanging. Instead, Einstein proposed that they are relative, meaning they can change depending on the observer and the conditions. His first major breakthrough came in 1905 with the special theory of relativity. This theory was based on 2 simple ideas. First, that the laws of physics are the same for everyone who is moving at a constant speed, and second, that the speed of light in a vacuum is always constant, no matter how fast the observer is moving. These ideas led to surprising conclusions. One of them is that time does not pass at the same rate for everyone. If a person moves very fast, close to the speed of light, time for that person slows down compared to someone who is standing still. This effect is called time dilation, and it has been confirmed by experiments using precise clocks. Another important result of special relativity is that space also changes. Objects that move at very high speeds appear shorter in the direction of motion. This is known as length contraction. Together, these effects showed that time and space are not separate and fixed, but are linked together in a single system called space-time. In this system, events are described using both space and time coordinates, and different observers may measure these coordinates differently depending on their motion. Einstein's famous equation, E equals mc squared, also came from this theory, showing that energy and mass are related and can be converted into each other. This idea later became important in understanding nuclear energy. Einstein did not stop there. In 1915, he introduced the general theory of relativity, which expanded his ideas to include gravity. Instead of seeing gravity as a force between objects, like Newton did, Einstein described it as a result of the curvature of space-time. According to this theory, massive objects like planets and stars bend the space-time around them, and this bending affects how other objects move. For example, the Earth moves around the Sun not because it is pulled by an invisible force, but because it follows a curved path in the warped space-time created by the Sun's mass. This idea was difficult to imagine, but was later supported by observations, such as the bending of light from distant stars as it passes near the Sun. General relativity also led to new predictions about the universe. It suggested that time moves more slowly in stronger gravitational fields, a phenomenon known as gravitational time dilation. This means that time passes slightly slower on the surface of a massive planet compared to a place far away in space. It also opened the door to the idea that the universe is not static but could be expanding or changing over time. Later discoveries confirmed that the universe is indeed expanding, leading to the development of modern cosmology. Einstein's work completely changed how scientists view time and space. They are no longer seen as fixed backgrounds, but as dynamic and interconnected parts of a universe that respond to matter and energy. This new understanding replaced Newton's model at very high speeds and strong gravitational conditions, although Newton's laws still work well for everyday situations. The theory of relativity showed that reality is more flexible and complex than previously thought, and it continues to play a central role in modern physics, influencing everything from GPS technology to our understanding of black holes and the origin of the universe. As Einstein's ideas became accepted, scientists began to explore the deeper meaning of space-time and how it behaves under extreme conditions. Space-time is not just a concept, but a real structure that can stretch, bend, and even ripple. One of the most fascinating outcomes of this understanding is the prediction of black holes. A black hole forms when a massive star collapses under its own gravity, compressing its mass into an extremely small region. This creates a point where the curvature of space-time becomes so strong that nothing, not even light, can escape from it. The boundary around this region is called the event horizon, and once anything crosses it, it cannot return. Black holes were once only theoretical, but today there is strong evidence for their existence, including images and observations of their effects on nearby matter. Another important idea that came from the study of space-time is that the universe itself is not static but expanding. In the early 20th century, scientists discovered that distant galaxies are moving away from us, and the farther they are, the faster they seem to be receding. This observation led to the conclusion that space itself is stretching, carrying galaxies along with it. This expansion suggests that the universe had a beginning, often described by the Big Bang theory. According to this model, the universe started from an extremely hot and dense state and has been expanding ever since. Time and space, as we understand them, also began at this moment, meaning that asking what happened before the Big Bang may not make sense in the usual way. Space-time can also experience small disturbances known as gravitational waves. These are ripples that travel through space-time, caused by massive objects accelerating, such as two black holes orbiting each other and eventually merging. For a long time, gravitational waves were only a prediction of Einstein's theory, but in 2015, they were directly detected by scientists using highly sensitive instruments. This discovery opened a new way of observing the universe, allowing us to listen to cosmic events that cannot be seen with light alone. The study of space-time also leads to strange and complex ideas, such as wormholes. A wormhole is a hypothetical shortcut through space-time that could connect two distant points. If they exist, they might allow travel between different parts of the universe much faster than moving through normal space. However, there is currently no experimental evidence that wormholes exist, and even if they do, they may not be stable or usable for travel. These ideas remain mostly in the realm of theoretical physics. As scientists explored these extreme conditions, they began to realize that Einstein's theory, while powerful, is not complete. It works very well for large objects like stars and galaxies, but it does not fully explain what happens at very small scales, such as inside atoms or at the very beginning of the universe. This limitation led to the development of another major branch of physics called quantum mechanics, which focuses on the behavior of particles at the smallest levels. The challenge of combining quantum mechanics with the theory of space-time remains one of the biggest unsolved problems in science today. As scientists pushed deeper into understanding the universe, they discovered that the rules governing very small things like atoms and particles are very different from the large-scale behavior described by Einstein's theory. This led to the development of quantum mechanics, a branch of physics that studies the smallest units of matter and energy. Quantum mechanics introduced a completely new way of thinking about reality, and it challenged many of the ideas about time and space that seemed clear before. At this level, particles do not behave like solid objects with fixed positions and paths. Instead, They exist in states of probability, meaning we can only predict the likelihood of where they might be, not their exact location until we observe them. One of the most surprising ideas in quantum mechanics is that particles can exist in multiple states at the same time, a concept known as superposition. For example, a particle can be in two different positions at once until it is measured. This challenges the classical idea that objects must have a single, definite state at any given moment in time. Another strange phenomenon is quantum entanglement, where two particles become linked in such a way that the state of one instantly affects the state of the other, no matter how far apart they are. This appears to happen faster than the speed of light, which seems to conflict with Einstein's theory of relativity. Einstein himself was uncomfortable with this idea and famously referred to it as spooky action at a distance. But experiments have repeatedly confirmed that entanglement is real. Quantum mechanics also changes how we think about time. In classical physics, time flows smoothly and continuously. But at the quantum level, some theories suggest that time may not be as simple. Certain equations in quantum physics do not clearly distinguish between past and future, raising questions about whether time has a fixed direction or if it emerges from deeper physical processes. Additionally, in some interpretations of quantum mechanics, the act of observation plays a key role in determining the outcome of an event, which leads to debates about whether reality depends in some way on measurement. When scientists try to combine quantum mechanics with Einstein's description of spacetime, they face serious difficulties. General relativity works extremely well for large-scale structures like planets and galaxies, while quantum mechanics works for tiny particles, but the two theories do not easily fit together. For example, inside a black hole, or at the very beginning of a universe, both quantum effects and strong gravity are important, and current theories struggle to describe these situations accurately. This has led to the search for a unified theory, often called quantum gravity, which would explain how space-time behaves at the smallest scales. Some modern ideas attempt to move in this direction. String theory suggests that the fundamental building blocks of a universe are not point-like particles, but tiny vibrating strings, and that space-time may have more dimensions than the four we experience. Another approach, called loop quantum gravity, tries to describe space-time itself as having a discrete structure, almost like a fabric made of tiny loops. These ideas are still being developed and tested, and there is no final answer yet. The introduction of quantum mechanics showed that reality is even more complex and less intuitive than previously thought. It forced scientists to question basic assumptions about time, space, and causality. Instead of being fixed and predictable, the universe at its deepest level appears to be uncertain and interconnected in ways that are still not fully understood. This ongoing effort to unify the laws of physics continues to drive research and may one day lead to a deeper understanding of how time and space truly work. The ideas of time and space may seem abstract, but they have very real and practical uses in everyday life. One of the most important examples is the Global Positioning System, or GPS, which is used in smartphones, cars, and navigation systems. GPS relies on satellites orbiting the Earth, each carrying very precise atomic clocks. Because these satellites are moving at high speeds and are also farther from Earth's gravitational field, time passes slightly differently for them compared to clocks on the ground. This difference is predicted by both special and general relativity. If scientists did not account for these changes in time, GPS calculations would quickly become inaccurate, leading to errors in location by several kilometers. This shows that Einstein's theories are not just theoretical ideas, but are essential for modern technology. Another major application is in the field of telecommunications. Signals sent through satellites, fiber optic cables, and wireless networks depend on precise timing and an understanding of how signals travel through space. The concept that nothing can travel faster than the speed of light sets a fundamental limit on how quickly information can be transmitted. Engineers must consider these limits when designing communication systems, especially for global networks and space missions. Even small delays matter when data is being transmitted across large distances. Time and space theories also play a crucial role in astronomy and space exploration. Scientists use these principles to calculate the motion of planets, predict eclipses, and send spacecraft to distant locations. For example, missions to Mars or other planets require extremely accurate calculations of position, speed, and gravitational effects. Without a deep understanding of how space and gravity work, these missions would not be possible. The same principles help astronomers study distant galaxies, black holes, and the overall structure of the universe. In the field of medicine, concepts related to time and precision have led to advanced technologies such as MRI machines. These machines rely on principles of quantum mechanics to create detailed images of the inside of the human body. While this may seem far removed from time and space theories, it is actually connected through the underlying physics that describes how particles behave. Accurate timing and measurement are also critical in many medical devices and treatments. Another important benefit is in computing and data processing. Modern computers, especially those used in scientific research, rely on precise timing to perform billions of operations per second. As technology advances, scientists are exploring quantum computing, which uses principles of quantum mechanics to perform calculations much faster than traditional computers. If successful, this could revolutionize fields such as cryptography, artificial intelligence, and complex simulations. Time and space theories also influence how we understand natural disasters and environmental changes. For instance, satellite systems monitor Earth's surface, track weather patterns, and predict storms. These systems depend on accurate measurements of time and position. Understanding how Earth moves through space and how its systems interact helps scientists make better predictions and potentially save lives. Beyond practical applications, these theories have changed how humans think about reality. They have shown that the universe is not as simple as it appears, and that our everyday experience is only a small part of a much larger and more complex system. This shift in understanding has influenced not only science, but also philosophy, encouraging people to think more deeply about existence, cause and effect, and the nature of the universe. Overall, the study of time and space has led to technologies that we use daily and has expanded human knowledge in powerful ways. What once seemed like abstract ideas have become essential tools for navigation, communication, medicine, and exploration. As research continues, these benefits are likely to grow, leading to even more advanced technologies and deeper insights into the universe. Even with all the progress made in understanding time and space, there are still major limitations and unanswered questions that scientists continue to explore. One of the biggest challenges is that the two most successful theories in physics, general relativity and quantum mechanics, do not fully agree with each other. General relativity explains gravity and the behavior of large objects very well, while quantum mechanics explains the behavior of very small particles. However, when scientists try to apply both theories together, such as in the center of a black hole or at the moment of the Big Bang, the equations break down and give unclear or conflicting results. This shows that our current understanding is incomplete and that a deeper, unified theory is needed. Another important limitation is our understanding of dark matter and dark energy. Observations of galaxies and the expansion of the universe suggest that most of the universe is made up of these unknown forms of matter and energy. Dark matter does not emit or reflect light, but its gravitational effects can be seen in how galaxies rotate. Dark energy, on the other hand, appears to be responsible for the accelerating expansion of the universe. Together, they make up the majority of the universe, yet scientists do not fully understand what they are or how they work. This raises questions about whether our current theories of space and time are missing something fundamental. The nature of time itself is also still a mystery. While we experience time as moving forward from the past to the future, many physical laws do not clearly explain why this direction exists. This is often referred to as the arrow of time. Some scientists believe it is related to the concept of entropy, which measures disorder in a system and tends to increase over time. However, This explanation does not fully answer why time feels like it flows in one direction, or whether this flow is a fundamental property of the universe or an emergent effect. There are also questions about whether time travel is possible. According to general relativity, certain solutions to the equations suggest that it might be possible to travel to the future or even the past under very extreme conditions, such as near black holes or through hypothetical structures like wormholes. Traveling into the future is already somewhat supported by the idea of time dilation, where time passes more slowly for someone moving at very high speeds. However, traveling into the past raises serious logical problems, such as paradoxes where cause and effect could be violated. As a result, most scientists remain cautious about the idea of backward time travel. Looking toward the future, many researchers are working on developing a theory of quantum gravity that would unify general relativity and quantum mechanics into a single framework. This theory could provide a deeper understanding of space-time at the smallest scales and explain what happens in extreme conditions like the early universe. Some approaches, such as string theory and loop quantum gravity, offer possible paths forward, but they are still being tested and refined. Advances in technology are also opening new ways to study time and space. More powerful telescopes, particle accelerators, and space missions are allowing scientists to observe the universe with greater detail than ever before. These tools may help answer some of the biggest questions, such as the true nature of dark matter, the structure of space-time, and whether there are additional dimensions beyond the ones we experience. In the end, the study of time and space is far from complete. While we have made significant progress, each new discovery often leads to even deeper questions. This ongoing journey reflects the nature of science itself, where understanding continues to grow but is never fully finished. The future may bring surprising breakthroughs that change our view of reality once again, just as Einstein's ideas once did. The study of time and space is not only a scientific journey, but also a deeply philosophical one, because it touches on how humans experience reality itself. While physics tries to describe time and space using equations and experiments, philosophy asks what these concepts really mean and how they relate to our perception. One of the most important questions is whether time and space exist independently of us, or whether they are partly shaped by the human mind. Some philosophers, like Immanuel Kant, argued that time and space are not things that exist out there on their own, but are forms of perception through which we experience the world. According to this view, the human mind organizes all experiences within the framework of time and space, making them essential for understanding reality, but not necessarily independent entities. Human perception of time is also very different from the way physics describes it. In everyday life, time feels like it flows continuously from past to present to future. We remember the past, experience the present, and anticipate the future. This creates a sense of direction or flow that seems natural and obvious. However, many physical theories do not require time to flow in this way. In some equations, time is simply another dimension, similar to space, without a built-in direction. This raises an important question. Is the flow of time something real in the universe, or is it something created by human consciousness? Some scientists and philosophers suggest that the feeling of time passing may be linked to how our brains process information and store memories. Space, too, is experienced differently by humans compared to how it is described in physics. We perceive space in 3 dimensions and understand distance and direction through our senses. But modern theories suggest that space may have more dimensions than we can directly observe. This means that our perception might be limited, giving us only a partial view of the true structure of the universe. In addition, our sense of space can be influenced by context, motion, and even emotions, showing that perception is not always a perfect reflection of physical reality. Another philosophical issue is the concept of reality itself. If time and space can change depending on motion and gravity, as Einstein showed, then different observers may experience reality differently. This does not mean that reality is completely subjective, but it does mean that it is not as fixed and absolute as it once seemed. The idea that measurements of time and distance can vary between observers challenges the intuitive belief that there is a single, universal perspective. The connection between time, space, and human experience also appears in questions about existence and meaning. For example, the awareness of time passing is closely related to the idea of life having a beginning and an end. This awareness influences how people make decisions, set goals, and understand their place in the universe. Similarly, the vastness of space can shape how humans think about their significance, often leading to feelings of curiosity, wonder, or even humility. In some traditions, including religious and spiritual perspectives, time and space are seen as part of a larger design or purpose. These views may interpret scientific discoveries in ways that connect physical reality with deeper meaning. While science focuses on how time and space work, philosophy and spirituality often explore why they exist and what they imply about existence as a whole. In the end, the connection between scientific theories and human perception shows that understanding time and space is not just about equations and measurements. It is also about how we experience the world, how we interpret reality, and how we find meaning within it. This combination of science and philosophy makes the study of time and space one of the most profound and thought-provoking areas of human knowledge. As scientific understanding has grown, new and more advanced ideas about time and space have emerged, pushing the boundaries of what we consider possible. One of the most widely discussed concepts is the idea of the multiverse. According to this idea, our universe may not be the only one that exists. Instead, there could be many universes, each with its own version of space, time, and physical laws. Some versions of the multiverse suggest that these universes are completely separate and cannot interact, while others propose that they may exist alongside each other in higher dimensions. This idea partly comes from attempts to explain certain features of our universe, such as why physical constants have the values they do, as well as from interpretations of quantum mechanics, where different outcomes could exist in parallel realities. Another advanced concept is the possibility of higher dimensions. In everyday life, we experience 3 dimensions of space and 1 of time, but some theories, especially string theory, suggest that there may be additional spatial dimensions that are hidden from our perception. These extra dimensions could be extremely small or exist in ways that we cannot directly observe. If they exist, they might help explain fundamental forces and particles in a more unified way. The idea of higher dimensions can be difficult to imagine, but mathematically it provides possible solutions to problems that current theories cannot fully resolve. The simulation theory is another thought-provoking idea that connects time, space, and reality. It suggests that what we experience as the universe might actually be a kind of simulation similar to a highly advanced computer program. In this view, time and space could be part of the system that controls how the simulation runs. While there is no direct evidence for this idea, it has gained attention because of advances in computing and the realization that complex virtual environments can be created. Some thinkers argue that if technology continues to advance, it might one day be possible to simulate entire worlds, raising the question of whether our own reality could be such a creation. There are also ideas about manipulating time and space for travel. Concepts like warp drives, which would allow faster-than-light travel by bending space-time, have been explored in theoretical physics. Instead of moving an object through space faster than light, a warp drive would compress space in front of it and expand space behind it, effectively allowing it to travel large distances quickly without violating known physical laws. Similarly, wormholes, if they exist and could be stabilized, might serve as shortcuts connecting distant regions of space-time. However, these ideas remain theoretical and would require forms of energy or matter that have not yet been discovered or understood. These advanced theories highlight both the creativity and the limits of current science. While they're based on mathematical models and logical reasoning, many of them are still far from being tested or confirmed. They often raise as many questions as they answer, challenging our understanding of reality and pushing us to think beyond traditional boundaries. At the same time, it is important to remain careful and critical when considering such ideas. Not all theories are equally supported by evidence, and some may remain speculative for a long time. Science progresses by testing ideas against observations, and until these advanced concepts can be verified, they remain possibilities rather than established facts. Even so, exploring these ideas is valuable because it expands our imagination and drives further research. It encourages scientists to develop new tools, experiments, and ways of thinking. Whether or not these theories turn out to be true, they play an important role in the ongoing effort to understand time, space, and the deeper structure of the universe. Throughout history, the understanding of time and space has evolved from simple observation to some of the most advanced scientific ideas ever developed. What began as basic awareness of day and night seasons and movement gradually turned into philosophical reflection, then mathematical description, and finally into modern physics with theories that describe the universe on both the largest and smallest scales. Early thinkers saw time as a repeating cycle and space as a fixed stage, while later philosophers questioned whether these concepts existed independently or only through human perception. With Newton, time and space became absolute and universal, forming the foundation of classical physics and giving humanity a powerful framework to understand motion, gravity, and the structure of the physical world. This view remained dominant until Einstein completely reshaped it. Through relativity, time and space were no longer fixed and separate, but became interconnected as space-time, flexible and influenced by motion and gravity. Time could slow down, space could bend, and gravity became a result of curved geometry rather than a simple force. These ideas were not just theoretical. They were confirmed through experiments and are now essential for technologies like GPS and modern space exploration. Einstein's work showed that the universe is far more dynamic and interconnected than previously imagined. As science advanced further, quantum mechanics revealed an even stranger reality at the smallest scales. Particles do not behave like solid objects with definite positions, but exist in probabilities, superpositions, and entangled states. This introduced uncertainty into the very foundation of reality and raised new questions about the nature of time, causality, and observation. When combined with relativity, these ideas exposed gaps in our understanding, especially in extreme environments like black holes or the early universe, where both quantum effects and strong gravity are important, but not yet fully unified. Modern science continues to expand these ideas into even more speculative but fascinating directions, such as dark matter, dark energy, multiverse theories, higher dimensions, and simulation hypotheses. These concepts attempt to explain the unknown parts of the universe that current models cannot fully describe. At the same time, they show that our understanding of reality is still incomplete and that the universe may be far more complex than what we currently observe or measure. Despite all these advances, one of the most important realizations is that time and space are not just external structures of the universe, but also deeply connected to human perception and experience. We do not simply observe time, we feel it passing. We do not just exist in space. We navigate and interpret it through our senses and mind. This connection between physical reality and human awareness makes the study of time and space not only a scientific pursuit, but also a philosophical and existential one. In conclusion, the history of time and space theory is the story of human curiosity pushing against the limits of understanding. From ancient observations to modern physics, each stage has revealed both answers and new mysteries. Time and space are no longer seen as simple backgrounds to reality, but as active, dynamic parts of the universe that shape everything within it. Yet, even now, the deepest questions remain unanswered. What is the true nature of time? What is space at its most fundamental level? And how does reality truly work at its core? These questions ensure that the journey is not finished. Instead, it continues, driven by the same curiosity that started it all.